So what we do here is this. We need to take a look at, we've talked about weak acids, we've talked about weak bases, but we need to figure out how are they connected. And so we've seen this before. We've seen both of these before, and we've done problems with them before. Ammonium, NH4+, it's a weak acid. Just a reminder how it's a weak acid. One, it donates one of its H pluses to form that H3O plus and NH3. And it's not one of the 7 strong acids, so it has to be weak. Down here, NH3 is a weak base. 1, it's not combined with a hydroxide. That's a big giveaway. 2, the hydrogen from H2O is donated. The H plus is accepted by NH3, making it a base. Again, not on the list, so it's a weak base. Now, if we notice too, before I get to start writing here, NH4 plus is a weak acid, like I said, and NH3 is its conjugate base. Okay, so just some things to keep in mind as we go through this. Now, I want to start out, and I like to start out all weak acid, weak base problems with our equilibrium expression. And so up top here, because this is a acid, I'm going to start out and say, hey, this is our Ka. And what we would have is NH3 on top times our H3O plus there, all divided by the concentration of NH4 plus. And we've seen that, we've done it. We're going to go down here to the base, and we're going to write the equilibrium expression for this weak base. So again, we're going to start out with Kb because it's a base. This is equal to what's on top, which is NH4 plus times that hydroxide, OH minus, all divided by just the concentration of NH3. Okay, again, everything we've talked about so far, we need a way to connect these. So here's what we're going to do. We are going to take our Ka, now I'll write it out to the side here, Ka times our Kb. And I don't need to write anything except what's next to or right of that equal sign. So for Ka, I'm going to write our components here in green. And so I'm going to start out here and I'm going to say, all right, NH3, the concentration, times the concentration of H3O plus, all divided by the concentration of NH4 plus, and then we're going to multiply that by our items here in our base dissociation constant. So now we're going to take this. We're going to say, all right, NH4 plus times our OH minus, all divided by the concentration of NH3. Now, again, we have its weak acid and its conjugate base, or vice versa here. And so when we multiply these across, something unique happens, and we can cancel quite a bit of things here, okay? And so if we do this here, and I take, and I look here and I say, hey, NH3 in green is on top and on bottom. Because they're diagonal, just like in stoichiometry or conversion factors, they are going to cancel each other out. And same thing happens with our NH4 plus. Okay, we have green NH4 plus on bottom and then purple on top. So we can cancel these out. And the only thing that remains is H3O plus times the concentration of OH minus. All right. Now we've seen this before. Does anybody remember if we have H3O plus times OH minus, it's equal to a unique K. Does anybody remember what that K is? So this K that I'm referring to is KW for water. So if we have a weak acid and its conjugate base, and we put this together, we can simply refer back to that KW, the K and the W being for our particular water. Okay? Question before we go on to the next slide? All right. So moving on here, we go through this. We have our next item here where I just rewrite this formula. And one thing I want you to remember is this. So product of acid dissociation constant and the base dissociation constant, multiply them together, is equal to KW. Now remember, and you get this on the AP appendix or the formula chart, and this is really important to start referring to that, but KW is equal to 1.0 times 10 to the negative 14th. And again, you get that value on the AP test, and you get it obviously on our test here. But those are things to connect together to think about here. So let me get this fired back up. And here we go, back in business. All right. So with this here, we can now start to use this and make more sense of it. All right. So here we go on this. Okay. We can now, if we are given the KA and we flip that chart over and that's not listed as a base, we can find the KB. Or if we're given the KB and it's not on that weak acid chart, we can find either of these, okay? So for number one, I'm gonna rewrite the formula that we just went over here, and that is KW is equal to our KA times our KB, okay? Now, as a reminder, KW, it's a constant. It's given at 1.0 times 10 to the negative 14th, and we will set this equal to our given Ka, which is 6.8 times 10 to the negative 4th. Okay, so we'll say this is equal to our 6.8 times 10 to the negative 4th times our KB. Now, how would we get KB? Very good. We're going to divide by this 6.8 times 10 to the negative 4th on each side. And so when we do this, we would take, again, 1 times 10 to the negative 14th, 1 times 10 to the negative 14th, divided by 6.8 times 10 to the negative 4th. And we had two significant digits here, so our KB ends up being 1.5 by the time we round, 1.5 times 10 to the negative 11th. Now, one thing I want to point out, hydrofluoric acid, relatively still a weak acid, but a relatively strong weak acid, times 10 to the negative 4th. There's only 3 zeros in front before we put the decimal. The Kb, in turn, because we had a fairly stronger weak acid, the Kb is really, really small, meaning we have a very weak conjugate base. All right. Now, if we go through this one down below here, I'm just going to start out and I'm going to say, all right, we have 1 times 10 to the negative 14th equals, this time we want to know, the problem says, hey, go find our Ka. And so we don't know Ka, but we do know we multiply that by our given Kb, which is 1.8 times 10 to the negative 5th. And once again, how do we get Ka? Divide, right? So 1.8 times 10 to the negative 5th. We divide that on both sides of the equation there. And we turn to our calculators to get the following number here. So 1.8 times 10 to the negative 5th. By the time we round again to 2 sig figs here, our Ka is just 5.6 times 10 to the negative 10. Okay. Point about this is that now if you look on your acid-base charts, and if you have the Ka, you can find the Kb no matter what. If you have the Kb, you can find the Ka, all because of this formula. Okay. Questions? Does anybody need this? Okay. All right. So now let's keep going further. All right. And so we have this item called pKa and pKb. All right. So with our pKa and our pKb, we have to start out and we have to look back at our Kw formula. So I'm going to go ahead and I'm going to start out and I'm going to say, all right, remember that Kw here, Kw is equal to our,
Ka times Kb.
yeah, thank you very much, Ka times Kb. Now, we did this earlier in our acid-base notes, but we want to make this number more useful. So what I'm going to do to both sides is I am going to multiply both sides by negative log, okay? By negative log, okay? Well, if I get negative log of my Kw, I can work with this, and we'll come back to this. And then this would be equal here to the negative log of our Ka times our negative log of our Kb. And we're going to really come back to this here in just a second. What I really want to concentrate on is this. Remember, Kw has a particular number. And I'm going to insert that. That's a known number here. And so instead of Kw, I'm going to say, let's go ahead and let's put in 1 times 10 to the negative 14th. We're still going to keep this stuff on the right-hand side as is, as negative log of Ka times the negative log of our Kb. And then I want to look at this, all right? Remember, this is normal logarithm here. And so all we have to do is I'm going to put this in my calculator, a negative log of 1 times 10 to the negative 14th. I press enter and I get exactly, on this side, I get exactly 14. Okay. Now, I'm going to pause here for a second and talk about yes.
Why is log negative?
So it has to deal with the powers of log. and how basically it's a base 10 system, which off the top of my head, I couldn't tell you, but it's because it's a base 10 system and that we're working with a negative exponent, which means decimals. So to make it a useful number, we put that negative out in front, because if you would try log with no negative, the same number here, I would get negative 14, which in essence, this helps identify our pH scale that we normally use, where 7's neutral, anything below 7's acid, above 7 is a base. But it's because our concentrations are so small. That's why we have that negative log, to make it a better number and then relate it to that logarithm. A good question. Okay. The other thing I want to point out is this negative log Ka and negative log of Kb. Okay. Well, negative log of Ka is simply equal to what we call pKa. Now, I've seen this before, because we've seen negative log of H3O plus is equal to our pH. Well, now we're just putting the P in front of the Ka, and we can do the exact same thing with the negative log of Kb, which is just equal to negative pKb. Okay? When we do this, what happens here? Logarithms. Log times a log, you'd have to go back to math rules. But what happens here is this. This would turn into the following. So all we're going to do is we're going to replace negative log of Ka with our pKa, because that's what it is set equal to, plus negative log of Kb is just pKb. And this plus that I put in right here, that comes from the rules of our logarithms. Again, that's more of a math question here. I just know how to insert it like that. When you take a log times a log, it turns into a positive or a plus value. Okay? Now, this is really useful, right? We've seen 14 before. We said 14 equals pH plus POH. Now we have a way to more effectively use these Ka and Kb values. Okay? Questions before I go to the next slide? All right, so what is the point about this? All right, the point about this, and I'll have you write this down and I'll explain it as I go here. If you look at pKa or you look at pKb, you can very quickly tell, hey, is this a strong acid, or I guess in this case, a stronger weak acid or a weaker weak acid? And the same thing can be said with our bases, okay? Just like pH is a really good scale. You guys told me right off the bat, hey, our pH, if I have anything less than 7, it's an acid. More than 7, it's a base. And if it's right at 7, exactly 7, it's a neutral substance in terms of pH. Same thing can be applied with pKa and pKb. We can look at it and we can say, hey, based on the pKa value, very quick snapshot, yeah, that's a stronger acid, that's a stronger base. Now, what I probably should have done here on all of these is inserted weak in front of stronger and or weaker, okay? So this would technically be a stronger weak acid, a stronger weak base, a weaker weak acid, and a weaker weak base, all right? Now, we're going to add some examples here right at the end that helps clarify and explain some of these items here to make just a little bit more sense, all right? But again, what the point about pKa and pKb, it's going to give you a very quick snapshot of, oh, that's pretty strong, that's pretty weak, and that's what these numbers mean here, all right? questions? Does anybody need this? All right, so last thing of the day here. We'll go pretty quickly since we know how to work through this, or we know how to use the formulas here. So we want to know all of these values, Ka, Kb, pKa, and pKb. Great. It sounds like a lot, but it really isn't once we get rolling here. I'm going to start out with acetic acid because it's on our acid dissociation chart. And if you look up acetic acid, it's the very first acid on our chart. The Ka for acetic acid is equal to 1.8 times 10 to the negative fifth. Now, we've actually seen this on our example problem here, but we can go ahead and we can solve for our Kb by using our formula 1.0 times 10 to the negative 14th equals our Ka, which we know from the chart is 1.8 times 10 to the negative fifth times our Kb. Now, you guys have told me before, okay, well, we divide by what Kb is attached. And once more, like I said, we've seen this before, but if we take 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative fifth, we get what number?
5.5 repeated.
Yep. And I'm just going to make that simple here. I'm going to call that our Kb. I'm going to just call it 5.6. I'm going to round up. Okay.
Times 10 to the negative 10.
Yep. 5.6 times 10 to the negative 10. Again, looking at that, especially with exponents, you go, oh, okay, maybe I can determine if it's weak or strong. But let's do this. Let's plug it into our pKa and really make use of this. All right. So we're going to start out with our Ka. And so our pKa, all our pKa is the negative log of that number here. Okay. So now all I'm going to do to find that pKa is I'm going to say negative log of 1.8 times 10 to the negative fifth. And I get a value here, I guess since we're using two significant digits here, my pKa is 4.7. Okay, we're going to come back and talk about this here in just a second. But now let's talk about our pKb. All right, pKb, the formula here is negative log of our Kb value, which is 5.6 times 10 to the negative 10th. I plug that into my calculator, say negative log of 5.6 times 10 to the negative 10th. And we might as well, this one rounds up. Our pKb is equal to 9.3. Okay. Now, here's the so what. If I replace pKa with pH, 4.7, yeah, that's a weak acid. All right. If I say pH is 9.3, you tell me that's a weak base. All right. So it gives you a really quick snapshot with this in mind. All right. Let's go. First off, any questions? Let's go really quickly and knock out this substance here. Now, aniline, it's not on this Ka chart. You'd have to flip it over to the backside. It's on our Kb value. In fact, it's the second one listed. And aniline, it is a weak base, okay? So because it is a weak base, our Kb is the value that's listed on the chart, and our Kb is 4.3 times 10 to the negative 10th. All right. Now, to find out our Ka, all we would do is we'd plug it into our formula where 1.0 times 10 to the negative 14th is equal to our Ka, which is something that we don't know. So we have Ka times our Kb, which is now 4.3 times 10 to the negative 10th. We go ahead and divide this number on each side. And we go through and we say this. 1 times 10 to the negative 14th divided by 4.3 times 10 to the negative 10th. And we get a value of 2.3 times 10 to the negative 5th. So our Ka is 2.3 times 10 to the negative 5th. Again, when I look at Ka and Kb, because it's a negative exponent, initially my mind can't go, yep, that's what I need to think about. That's what I need to have or know if it's an acid or base or a stronger acid or base. So we do the same thing. We start out here. We want to find pKa. I'm going to use our value over here on the right. And so our pKa is equal to the negative log of this value here that we just took the time to find, 2.3 times 10 to the negative 5th. Okay. And so if I take and I say negative log times 2.3 times 10 to the negative 5th, I press enter, rounding to 2 decimals here, I get a pKa of 4.6. Okay. If I do the same thing for pKb, I do this. So pKb, this time we're going to use that first given value from the chart is equal to the negative log of 4.3 times 10 to the negative 10th. I plug that into my calculator, negative log 4.3 times 10 to the negative 10th. I press enter. Rounding here, I get a pKb of 9.4. Okay. Again, the point about this is it gives you a much clearer snapshot of saying, yep, this is a relatively weak base. Yep, this is a relatively stronger weak base. It gives you that quick perspective is what I'm trying to say here. All right, questions?